Hello everyone, this is Dr. Webb. In the last video we had a brief introduction into vector functions when we used some vector functions to write equations for lines. But in this video we're going to be taking a much deeper look into it and be looking at how to represent all sorts of different curves as vector functions, both in R2 and in R3. So when we're looking at curves in R2, the curves that we're most familiar with look something like this. And so these are the curves where the y-coordinate is some function of the x-coordinate. So y equals f of x for some function f. But certainly that does not represent all types of curves that we can have. In fact, really it's very few. These are having y be a function of x is actually very restrictive because it means we can only have one y value for each x value. Whereas if we think about curves in general, they look more like this, and they can double back on themselves, and they can go all the way around. And so this is the type of object that we're really going to be trying to parameterize today. Something in this wild red stuff rather than the very tame f of x stuff. And so obviously we're not going to be able to write this just as y is equal to some function of x, and so we're going to need to use and try something else. And so what we're going to do is we're going to use these vector functions to what's called parameterize the curve. And so what exactly is a parameterization? So a parameterization of a curve is a representation of the curve where each coordinate is represented separately as a function of another variable, non-spatial variable. Usually we'll use t, and this t is what's called a parameter, right? And so you can kind of think about t as representing time. And so rather than, when you think about y equals f of x, y and x, these are both coordinates. These are talking about coordinates, and they're being related together in one equation. What a parameterization is going to do is break these apart. So for a parameterization, we're going to be thinking about things separately as we have some function x of t, where this is only some function of t, y of t, and we're treating the two coordinates separately. Okay, and so if we're doing this in R3, say, you'd have three separate functions, one for the x-coordinate, one for the y-coordinate, and one for the z-coordinate. And for every value of t that you pick, you plug that into each of those functions, and that gives you 1 point on the curve. And then as you change over a range of values of t, that's going to draw out the curve for you. Okay, so if we're thinking about some curve, let's do this in R2. There's our x-axis, there's our y-axis. Let's pick some sort of simple curve like this that's not a function. So what we're going to do is we're going to take some parameter t and set t values where we look at the two coordinates separately. And so we'd be paying attention to what x is, and then we'd be paying attention to what y is. And then we go separately, go to some other time point. That would give us some other x value and some other y value. And then we pick some, so this would be at t1, t2, another point, call it. So let's say this is happening at t3. Have another x value, another y value, and as time goes on, we'll just be marching down on this curve, keeping track of what the x and the y values are separately. Right? So you can kind of think about what this parameterization is doing is it's sort of like, if you've ever seen sort of a map on, say, Google Maps, and you move around, then it treats how you move in your longitude and latitude separately. And so this is sort of the exact same idea. Right. So let's talk about some vector function parameterizations, some of which these are you've already seen. And so first of all, lines. So we have R of t. Equation for the line is going to look like x naught plus a times t, y naught plus b times t, right? And so where x naught, y naught is a point on the line, and the vector AB is a vector on the line, then this R of t is going to draw out this line, right? And so, like, for example, let's make this tangible as possible. Let's say R of t is 2 plus 3t, y is 1 minus 4t, right? And so this is a line that goes through the point 2, 1 and along the vector 3 minus 4. And so if we pick different t values, we plug in 0, we're going to get back 2, 1, the point that we started with on the line. If we set r to be 1, well, we get 2 plus 3 is 5, 1 minus 4 is minus 3, and so that's another point on the line. And so we looked at this in the last video. Circles. This actually is something that we haven't called it a parameterization, but you were actually very familiar with this. So let's start off with the unit circle. And so if this is the unit circle, how do we think about points on the unit circle? Well, often we think about them as being, breaking it down into cosine and sine of some angle. Well, deep down, what's going on here? Well, this is a parameterization of the circle in terms of the angle that we're going up at, right? And so if this theta here is a parameter. And so as theta ranges from 0 to 2 pi, we're drawing out the entire curve of this circle. So what if we want to do this for circles centered somewhere else, right? So rather than being centered at 0, 0, we want to be centered somewhere like, actually, yeah, let's do it centered somewhere else. So let's say this is something like 8, 5. How could we do a circle with radius 1 centered at 8, 5? Well, what we could do is we just want to shift this entire circle by 8, 5. Right? And so if we just do cosine, sine theta, sine theta, that's drawing out the unit circle. And then we're going to shift it by 8, 5, and that's going to move everything over to the other side. Right? And so looking at this, we'd have r of t is equal to cosine theta plus 8 sine of theta plus 5, and that's going to give us our parameterization. Okay, now this is what I'm telling you it is. How can you believe me that this is true? Okay, so let's get rid of this. Let's start back with that parameterization I gave. Cosine of theta plus 8, sine of theta plus 5. And my claim is that this will draw out a circle of radius 1 centered at 8, 5. Okay, and so looking at this, my x-coordinate at any time t, let's make that t, cosine t, sine t, cosine t, sine t. Okay, so my x-coordinate is cosine t plus 8. My y-coordinate is always going to be sine of t plus 5. Okay, so then if I move the plus 8 and the plus 5 to the other side, I'm going to have x of t minus 8 is equal to cosine of t. Y of t minus 5 is equal to sine of t. Okay, well, from the Pythagorean theorem, I'm going to know that cosine of t squared plus sine of t squared is always going to equal 1. Well, we've got that cosine of t is equal to x minus 8. And so that cosine squared is my x-coordinate minus 8 squared plus sine is equal to y minus 5. So sine squared is going to be y of t minus 5 squared equal to 1. And so for any fixed t, this x of t is talking about an x-coordinate. Y of t is talking about a y-coordinate. So what's happening here? Well, my x-coordinate minus 8 squared plus my y-coordinate minus 5 squared is equal to 1. This is the equation for a circle with radius 1 centered at the point 8, 5. Okay, so that works exactly the way we want it to. What if we want to do a different radius? So let's spice this up a little bit more. Let's find circle with radius 3 centered at let's say minus 1, 2. Okay. So if I had r of t be cosine of t minus 1 sine of t plus 2, this would be a circle with radius 1. I want this sine and cosine to be going, rather than just 1 out, I want them to be going 3 out. And so I'm going to tuck that 3 in to the 3 cosine, turn it from cosine to 3 cosine, and turn it from sine to 3 sine. And now my claim again is that this is going to be a circle. This is going to give me the equation for a circle with radius 3 centered at minus 1, 2. Okay, and so let me convince you about that. So same as before, I've got x of t is equal to 3 cosine of t minus 1. And so if I solve for cosine, I'm going to get x of t minus 1 divided by 3 is equal to cosine of t. I've got y of t is equal to 3 sine of t plus 2. So solving for sine of t, I have y of t minus 2 over 3 is equal to sine of t. And so then using that same trick, that cosine squared plus sine squared is equal to 1, what am I going to end up with? Well, I have x of t minus 1 squared over 3 squared is 9, plus y of t minus 2 squared, also over 9, is going to equal 1. Right? This is cosine squared. This is sine squared. And looking at this, I have 9s on the denominator on the left. And so if I just multiply everything by 9, I'm going to get my 1 here is going to turn into a 9. These disappear. What are we left with? X minus 1 squared plus y minus 2 squared equals 9. That is the equation for a circle with radius 3 centered at minus 1, 2. Okay. So what's the general rule here? So if we want to do a vector equation for circle centered at x naught, y naught, with center centered at x naught, y naught. I already put the center in. We just need to pick the radius. Let's call the radius r. Well, the vector function for that, following the same thing we did before, is going to be, we can write it as r cosine of theta plus x naught, r sine of theta, not theta, I should be using t's, even though t is talking about an angle here, r sine of theta plus y naught. That's going to give me my parameterization. And so in breaking this apart, the plus x naught and the plus y naught here, this is shifting the center to x naught, y naught. So literally I'm taking the whole curve, shifting it to x naught, y naught. And then the cosine and the sine are drawing out a circle. If it was just cosine and sine, it would be drawing out a circle of radius 1. To get the radius bigger, that's what the r is doing. So the r is controlling how big. Cosine and sine are drawing the circle. R is controlling how big the circle is. Okay, and so this is the general formula for getting a parameterization for a circle. Okay. So the functions that we could draw nicely before, the form y equals f of x, it also is easy to write these as vector functions. And there's a quick trick to doing this. You're going to set the x coordinate to just be t. And so then y of t from the function is going to be f of what the x coordinate is, but we just set the x coordinate to be t itself, and so that x of t is just f of t. Okay, and so our vector function parameterization is going to look like r of t, t, comma f of t. And that always works. Okay, so here is a vector function. R of t is t cosine of t, comma t sine of t. And let's try drawing this out for t greater than 0. Okay, and so the way we're going to do this is we're just going to start by plotting points. Right, so let's look at this. Let's look at values of t, what x is going to be, and what y is going to be. So we're starting at t equals 0, so let's start off with 0 there. Well, so then for the x coordinate, it'd be 0 times cosine of 0. Well, 0 times anything is 0, and same thing for the y coordinate. So at t equals 0, I'm starting at the origin. So there we are at t equals 0. Let's see, so since we're doing this Since we've got trig functions, let's have our next one be pi over 6. Right? So it would be pi over 6 times cosine of pi over 6. Well, cosine of pi over 6 is a half. And so that would be pi over 6 times a half would be pi over 12. And no, cosine of pi over, that's not right. Cosine of pi over 6 is not a half. It's square root of 3 over 2. So I need to put a square root of 3 there. Sine of pi over 6 is 1/2. So it's going to be pi over 2. And so that's going to be, well, so it's going to be on, it's going to be up about pi over 6, but it's going to be pi over 6 out. So pi over 6 is a little bit less than a half. So let's say it's about right there. At pi over 4, we'd be at, so cosine and sine of pi over 4 are both 1 over square root of 2. And so this would be pi over 4 times square root of 2. Pi over 4 times square root of 2. And so that would be a little bit further out. Let's do pi over 3. And at pi over 3, now cosine of pi over 3 is 1/2. So this would be at pi over 6. And this one would be at pi over 6 times the square root of 3. And so that would be something like there. Pi over 2, cosine of pi over 2 is 0. Sine of pi over 2 is 1. And so this would be at the point 0 pi over 2, which is up there. And so you can kind of see these to pi over 2. If you connect these together, it's going to go like that. Rather than going through all the points, I'm going to jump right up to pi. So at pi, cosine is -1. And so I get minus pi there. And sine of pi is 0, so I'd have 0 there. And so if that's pi over 2, then this would be at pi. And so this would curve out to there. And then if we did 3 pi over 2, well, 3 pi over 2 cosine 0 again, and sine would be -1. So this would be somewhere way down here at 3 pi over 2. And so we can kind of get a sense for what this curve is drawing out. And so it is actually drawing out a spiral that's going out further and further. And in fact, in this spiral, if this is at time t, then the distance from the origin to the point on the curve is precisely t, right? And how can we be sure about that? Well, if we use the distance formula on this, the distance formula from the origin, we'd have t cosine of t squared plus t sine of t quantity squared is equal to the distance squared. And so squaring this out, I could factor out a t squared from both of these. Have cosine of t squared plus sine squared t equal to the distance squared. Cosine squared plus sine squared, that's equal to 1. And so my t squared is my distance squared. So my distance away is t, since t is positive. Okay, so this is the parameterization for drawing a nice spiral. If you wanted to try and do this with functions, well, first of all, you'd have to break it up an awful lot. So just noticing in the first half, just from as t goes from 0 to pi over 2, it already backs over on itself once. So you'd have to break that up into 2 separate functions. And then once you get to pi, it crosses over itself again. So it would just be a huge headache. So this is an example of a function that's much better to write as a vector function as a parameterization like this. Okay, so the last one we were given a parameterization and told to draw it out. In this one, we're given a curve, we're given a function for an ellipse, and we want to find a parameterization for this. Okay, so our curve here is x squared over 9 plus y squared over 16 equals 1. Okay. So the trick for this one is we're going to do kind of the opposite of what we did to find the parameterization of a circle. Right, so then that one I said, start off with the sines and cosines. You can come back and see that it's a circle. Well, in this one, we're going to start off with this here, and we're going to translate it into sines and cosines. Right, and so you can kind of see here I have x squared over 9, so that's something squared, plus something else squared equals 1. Something squared plus something else squared equals 1. Well, what I'm going to do is I'm going to set the first term equal to cosine of t, the second term equal to sine of t, and solve out what x and y have to be. Okay, so let's do that. Actually, I should say I'm setting this equal to cosine squared, and this one equal to sine squared, so it matches the Pythagorean theorem. Okay, so if x squared over 9 is equal to cosine squared, well, that means x over 3 is equal to cosine, and so I'm going to set x to be 3 cosine t. Y squared over 16 is equal to sine squared. Well, that means that y over 4 is equal to sine, and so y is equal to 4 sine t. So now we have our x and our y, and so our parameterization for this is going to be 3 cosine t, 4 sine t, and because we got it from working on this equation, working backwards, we're going to end up that this is going to draw that out. Okay, so we have, that's our vector function parameterization for this ellipse. All right. Okay, so R2, we're just dealing with things on the xy plane. R3, things are getting a little bit funkier. Okay, so now we're given a vector function in R3. So R of t, the x component is just t, the y component is cosine of t, and the z component is sine of t. So to start getting a handle on this, let's do the same thing we did before, but now we have to worry about 3 coordinates. So t, x, y, and z. So let's start at 0 again. So if t is equal to 0, x is equal to 0, y is equal to 1, z is equal to 0. And so that's talking about the point 0, 1, 0, which is right there on the xy plane. Let's let t equal, let's jump up to pi over 2. So pi over 2, y is also pi over, or x is also pi over 2. Y, cosine of pi over 2, that's 0, and sine of pi over 2 is 1. So that point is going to be, we're going to go out pi over 2, and then up 1 from that. And so then the curve has kind of come over like this between those two. If we then go to pi, we're going to be pi out. My y, cosine of pi, is now minus 1. Z is going to be 0 again. And so if that's at pi, then my y is going to be out at minus 1, z 0. And so we kind of come back down around there. If we go to 3 pi over 2, then x is going to be 3 pi over 2, y is going to be 0, z is going to be minus 1. And so that would be there, go down. Okay. And so what is this starting to trace out? Well, this is like a spiral. It's not really a spiral so much. It's going around the outside of a cylinder. In fact, if you look, each of these points are exactly one away from the x-axis. That's one away from the x-axis there. That's one away from the x-axis there. That's going to be one away from the x-axis there. And so as this goes around, it's staying exactly one away from the x-axis, but it's spinning around it. Right? And so how can we see that that has to be happening? Well, we've got our cosine and sine right there. Right? And so if we ignored the x-coordinate completely, the y and the z-coordinate are giving us y squared plus z squared equals to 1. And so this is ignoring the x-coordinate. Well, y squared plus z squared equals 1. This is drawing out a cylinder of radius 1. As we go through, and then when we bring the x-coordinate back in, it's just saying to pick one point. Rather than drawing out the whole curve, it's only picking out one point for each x value. And so that's how it's drawing that curve spiraling around. Okay, so we just drew out a curve in R3. So now we're going to be given a curve in R3, and we have to find a parameterization for it. Okay, and so curves in R3 coming from equations, if you take a single equation in R3, it's not going to draw out a curve, it's actually going to draw out a surface. Okay, so to get a curve in R3, what you actually have to do is if you want to do it with equations, is you have to find an intersection between two surfaces that give it. Right? So if we're talking about curves in R3 coming from equations, these are coming from the points that satisfy two separate equations. So in this one, we're taking the cone x squared plus y squared equals z squared, and the plane z equals y plus 4. So let's see if we can quickly sketch what this looks like. Okay. So the curve z squared equals x squared plus y squared. So one way to kind of envision what these surfaces look like is to kind of think about what they look like on some of the coordinate axes. And so if I take the xz coordinate axis, I'm going to focus on the cone first. The xz coordinate axis, so I'm setting y to be 0. It's going to look like x squared equals z squared. And so that simplifies down to x is going to equal to plus or minus z. And so that's giving me two lines, x equals minus z and x equals positive z. Okay. Same thing if I take out, let's do this in a different color. If I take out look at the yz plane, so set x equal to 0, I get z squared is equal to y squared. And so that's going to tell me that y is equal to plus or minus z. So these lines are going to start looking like they copy over each other. Okay. And then lastly, now I have sort of an idea for sort of what it looks like horizontally going up and coming towards me going up. I just have to get a kind of an idea of what horizontal cross sections look like. And so a horizontal cross section is setting z to be some value. And so if I set z to be some value, like if I set z to be 1, if z is equal to 1, then I have 1 squared is 1 is equal to x squared plus y squared. That's giving me a circle of radius 1. And so it's kind of coming around as a circle there. And so there's our cone. So our cone is right there. Okay, so now for z equals y plus 4, well, that's drawing out on the yz plane, that's drawing out a line. Goes from 4 to 4 like that. And so then this is going to cut through. And so on the yz plane, it's cutting through like that. And then it's going to go kind of up like this. And I know this is a beautiful picture. So this looks like, I think this is going to look kind of like a skewed ellipse on its side. Okay, so that's roughly what it would look like. This is actually a case where oftentimes the actual going through the algebra actually might give you a better picture of what it is than trying to roughly draw a picture. So let's do that. So drawing a picture for this guy, coming up with a vector equation. Okay. So this one right here, this plane right here, gives me z in terms of y. Right? So I'm going to use that and plug that into my equation for the cone and see what I get. Okay. So I'm just remembering I'm setting z to be equal to y plus 4. And so then when I plug that in, I'm going to get y plus 4 squared is equal to x squared plus y squared. Oh, I was wrong. I don't think this is an ellipse. Let's see what we get. So if I square this out on the left, I get y squared plus 8y plus 16 is equal to x squared plus y squared. Now if you notice, we have y squareds on both the left and the right. So I can cancel those out. And I'm left with 8y plus 16 is equal to x squared. And so let's solve for y there. So I'll have 8y is equal to x squared minus 16. Now we divide by 8 all the way across. And we get y is x squared over 8 minus 16 over 8 is 2. Okay, so now take a look at this. So we've written y now in terms of x, and then we have z written as a function in terms of y. So when we want to do the parameterization of this, if I start off defining x, then that's going to define y. And then once we have y defined, that's going to define z. So what our parameterization is going to be is we're going to let x, the x function, just be t. Then the y function, in place of x for our y function, we're going to put in t. And so we get t squared over 8 minus 2. And then for the z function, we're going to plug our y function into y plus 4 equals z. And so z is going to be y plus 4, which will give us t squared over 8 plus 2. And so now we have our 3 functions for each component. So we can write out our vector function. R of t, x component is t, y component is t squared over 8 minus 2. Z component is t squared over 8 plus 2. And so now that we have this parameterization written out, now I can figure out what shape it's going to be. And this shape, in fact, is going to give me a parabola. And so why do I know it's going to be a parabola and not something like an ellipse? Well, it's from looking at this x-coordinate. The x-coordinate's just t. And so it's never going to wrap back on itself. The x-coordinate's just going to continue going out in one direction. And so it can't close on itself like an ellipse does. And also, what we have here is we have a cone with a plane sliced through. And so this is what's called a conic section. And there are really the types of shapes you can get from a conic section are either circles or ellipses, or hyperbolas or parabolas. And looking at this, since it can't be a circle or an ellipse, and it also can't be a hyperbola, because the x value says this is all going to be in one piece, not in two pieces like a hyperbola is. So this has to be a parabola. So this is a case where actually doing the algebra and looking at what you have at the end, this gives you a much better idea of what the actual curve looks like than trying to carefully draw it. Basically, it's really difficult to draw this well enough to get a good idea of what the shape is. And that is it for this video. I will see you later. So that is all I have for this video. I will see you again soon.